We can start now. Very good afternoon, everyone. So today we are happy to have Dr. Ashwani Pandey. He's from Haldwani, and he also did his PhD from Aries Nainital. So he completed his PhD in 2019 from Aries, and then he was here for 2 more years during the COVID time. Then he moved to IIA Bengaluru for roughly about 1 year for a postdoc. And then he moved to Poland. This institute, I cannot pronounce properly the name of
this one.
DXCDT, CFT, something like that.
CFT.
So he stayed there for about 2 years, and then he recently moved in 2024 to Institute of High Energy Physics in Beijing as a visiting scientist. So he stayed there for 6 months, and he's going to take up another position as a postdoctoral researcher in University of Utah in USA. So before that, so he's visiting here for a short time. So he'll talk about mostly about his work of research work. So mostly related to AGNs, but today he'll talk about the theoretical FE2 templates of bright quasars. So Ashwani, you can start your presentation.
Okay. Thank you. Thank you for the introduction. And thank you for having me here after a long time. And today I will talk on a different topics. Like I did my PhD on quasars, a class of AGN. But today I'll be talking about iron emission or the Fe2 emission in AGNs in general. Okay, by the way, I was postdoc in CFT. This is CFT. And this logo is very interesting. So this is a tree, and the apple is falling from the tree. You might know the Newtons. And this PAN means the Polish Academy of Science in Polish. And this is, this logo is from the Institute of High Energy Physics, where I am visiting as a visiting scientist under with this Pi 5 fellowship. Okay, I see many young people here. So maybe you might know about AGN or active galactic nuclei. If not, I can give you a brief introduction. So AGN, so this diagram shows what we know currently about the AGN. So its main components. You can see at the center, this black dot is the black hole, supermassive black hole, with mass around 10 to the power 6 to 10 to the power 9 times solar mass. Then this black hole is accreting material from the accretion disk. And then we have those clouds type structures. Basically, these are the gas that is also moving around the this center part. Then we have this torus-like structure, which is made of dust, called dusty torus. And there are regions with at a distance of 100 parsec. These are narrow line regions. In some AGNs, you can also see an outflow of particles, which we call the relativistic jets. And accordingly, AGN can be classified as radio loud and radio quiet. But today I'll be focusing on radio quiet sources mainly. And among radio quiet sources, mainly on radio quiet quasars. So the quasars are the AGN with luminosity greater than 10 to the power 45. And these definitions are there, but I'll explain what are these broad lines and what are narrow lines, because I will be using these. So the broad line means when the width of the line or the FWHM is greater than 1,000 kilometers. It's broad line. And if the width is less than 500 kilometers, it's narrow line. Then I will be using the term narrow line Seyfert 1. It's actually a Seyfert 1 galaxy or the radio quiet quasars, which has broad lines and narrow lines in their spectra, but their width is around 1,000 to 2,000. So that's why it's called narrow line Seyfert 1, because its line width is narrower than the most of the other quasars. This is the mean spectra of quasar. So the question is, how will you distinguish an AGN with a normal galaxy? The answer is you see their spectra. If you see the spectra of a normal galaxy, it has a underlying black body spectrum, which is mainly from the stars, and then you can see some lines. If it is a young galaxies, spiral galaxies. If it is an old galaxy, you will see absorption lines in the spectra. But in the active galactic nuclei or the active galaxies, the spectra has underlying power law continuum, and the lines, emission lines, are broad. It's broader than the normal galaxies. In normal galaxies, lines are broader because of the thermal broadening, the temperature, which is of the order of 10 kilometers per second. But in active galaxies, this broadening can be much higher, like 1,000 kilometers. And how these lines are formed? So in this diagram, we have this central part, accretion disk, and sometimes the corona. So I will call both as a central part combined. So the radiation from the center part, it photoionizes the gas in this broad line region. And that's why we have the lines in the spectra. And the line width of spectra is much higher, like 1,000 kilometers per second. But because of the thermal temperature, the line width can be 10 kilometers per second. So the broadening in the spectra of quasars is not because of the thermal broadening, it's because of Doppler broadening, which is because of the motion of the gas from which the lines are produced. But the next thing is, we don't know much, or we do not understand fully how that gas which is producing lines is distributed in the active galactic nuclei. What is the distribution? What is their dynamics? What are their kinematics? There are models, like some models propose that the gas can be distributed in the form of clouds. And there are other models in which gas is in the form of the winds from the accretion disk. So this part, BLR, broad line region geometry, dynamics, and kinematics. This is my main or broader research interest. But today I'll be talking about a very small part of this, like the small part of broad line region, which is mainly focused on the emission, iron emission, like the gas which is producing the iron emission.
हाँ, दोनों में जाके जैसा वीडियो में बोला था, मतलब पहले एक वो आ रहा है इंटरेक्टेड करके, फिर एक स्क्रीन आ रही है, फिर बंद हो रही है, फिर खुल रही है।
Whoever is online, can you please mute yourself?
आपको लैंग्वेज सेलेक्ट करनी है और उसके बाद सॉफ्टवेयर अपडेट करना है, तो इसमें यहाँ पर आके स्टॉप हो जा रहा है। ओहो, मतलब ये फर्मवेयर अपग्रेड हुआ नहीं इसका, है सर?
No. If it is Doppler broadening, then it's because of the motion. Yeah. Yes. Yeah, it's combination. Yes. Okay. So, but there are like wind models in which
always seen. Okay, it is seen at a certain time. So suddenly you see a shift, right? A certain Doppler, some shift in the
inflow and outflow means, yeah, shift in the peak of the line.
Yes. So then something is happening now, right?
Yes.
Something is moving. And winds are in general, what starts, it loses, right? It leaves the object.
Yes.
Right. For example, solar wind, it leaves the sun and comes here and passes us. So the people who are proposing that model, that it's because of the winds, how do they justify it?
So I can tell you about one model which I worked on, like it's the Fredo model. Fredo. Yeah, it's a field relatively accelerated disk winds, a disk outflows. So what happens from the accretion disk, the wind, because of the radiation pressure, it moves the dust or dusty clouds, So you will see a kind of wind or upward motion. Yeah, yeah, it's radiation driven winds actually. Yeah, yes. So you will see some kind of that the cloud is coming towards you. So it will be a kind of outflow. But then when it so now there are two situations. Can I use the board? Okay. Okay. So if this is the disk and here is the black hole or the center part, and if the cloud is like from the radiation pressure, it moves up. But the disk in this part, it's shielded. This cloud is shielded from the disk because disk is thin there. So here you will so the cloud moves upward when it comes direct contact of the radiation. So the cloud, because it has the dust, so the dust will evaporate. I mean the center part, not the black hole. Yeah. So that time, like this radiation will sublimates the dust in that cloud, and you will see then that this you will see that this cloud will fall down. So in this direction, this will be the upward motion or towards the observer. So the outflow when it goes down, yeah, this is the field wind. Yeah. Mm-hmm.
The time for time gap for the radius of
Mm-hmm.
or microwaves are just about equal to
Mm-hmm.
but these lines are your
Yes. Yes.
and wherever it goes,
Yes.
very, very
Mm-hmm.
long. So can it be something as transient as wind in line, or whether it was
But with yeah, but with rotating there is problem. Like there is a means continuous observations where we see outflow in the C4 line, carbon 4 line. Yeah. So if it is a in the form of a disk, then it's very difficult to explain that thing. Yeah, but then how will we explain the outflow?
that outflow picture you can see the profile of the line.
Yes. Or in the if you do the velocity resolved reversal mapping.
But what he is saying, and that is basically providing this. You are not saying that the origin of the lines are the wind.
No, 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 no. No. Yeah, these are there always. Okay, so okay, so here I will be mainly focusing on the reason or the part of the BLR that is producing iron emission, and mainly the singly ionized iron emission, that is Fe2. And why? Because this has so many transitions, and you can see this Fe2 in the spectra from UV to NIR in whole range. And sometimes they are so close that they form a blends, and that is called the pseudo blends, pseudo continuum. So in this spectra, these red vertical lines, this indicates the region where you see most prominent Fe2. And I have mentioned the wavelength range, which is most prominent. So you can see in the spectra easily these lines. And this is in the UV part, and this is in the optical part. This region, this is called lambda 4570, and this is lambda 5340 in this part. And here, this is actually the composite spectra of quasars. And you can also see in the individual spectra of the of the sources. Like this is the spectra for narrow line Seaford 1, ARK564. Here, because it is a narrow line Seaford 1, it has very strong Fe2 emission. So you can easily see Fe2, and you can easily identify some of the components in Fe2 because it's narrow line quasar. So you can see here, this Fe2 is this part. In here, this is lambda 5300. And those 42, 48, these numbers are actually the multiplet, iron multiplets. So now the question is why Fe2 is so important? Because Fe2 you can see in the spectra throughout the from UV to NIR. So it contributes most significant part in the spectra of quasar, which is around 25%. 25% of total BLR energy. Second thing is it affects the other individual lines like H beta MG2. So that you need to estimate the Fe2 contribution very accurately. Otherwise, you will have wrong estimation of the other lines, and that will affect the other parameters like the black hole mass and other things. Third thing is it anticorrelates with the H beta FWHM and the O3 emission, which is called the eigenvector, and that forms the basis for quasar main sequence. This plot is the quasar main sequence, which basically divides the quasars into two categories: population B, this one, which has FWHM of H beta above 4,000 km per second, and population A, for which the FWHM of H beta is less than 4,000 km per second. And this has a physical basis because if you see in population A, their H beta line profile has a different shape, like the Gaussian. And for population B, their H beta line profile has a Lorentzian profile. This RFE2 is actually the ratio of FE2 in the optical part in this range. And the ratio, its ratio with H beta intensity. Okay, so also these population A sources, they are very high accretors. That means they have higher interratio. And when this RFE2 value is greater than 1, they are called extreme population A sources, XA. They have high interratio, and they also have very high ion emission. So what are the open questions regarding this Fe2 emissions? First one is their location, where the Fe2 emitting gas is located in the BLR. So the proposed scenarios are like Fe2 emission, it can be coming from the same region from where we are getting H beta line. But then there are other theories which says that it could be at the distance double the H beta line. And then there are also theory that it could be from the region which is intermediate from the H beta line and the torus, between the torus. Second question is, what is the excitation mechanism for Fe2 emission? So two excitation mechanisms are there. First is the photoionization mechanism and the collisional excitation. So in photoionization, the proof is that we can see in the reverberation mapping studies, there is a very good correlation between the continuum and the lines, emission lines, like the Fe2. But then there is a problem. So when we use these photoionization models, we found that the model predicted UV to optical Fe2 ratio is always greater than the observed ratio. And it's greater than by a factor of the observed ratio is around 2, but the predicted ratio is more than 10, 20, or can be 100. So this is the first, the major issue. But to solve this issue, Gary Ferland, they have suggested that it's possible that the Fe2 that we are getting is coming from the dark side of the cloud. Okay, let me explain what is the dark side. So if so if there is this is the center part, and you have the cloud here. So the radiation is coming in this part. This is called the illuminated side or the bright side of the cloud. But the other side is called the dark side or the cellular side. And you also have the cloud other side of the black hole. So when observer is here, he will see radiation from the dark side, also from the radiation from the illuminated side of the cloud. So to explain this mismatch between the UV to optical ratio predicted and the observed ratio, they suggested that the observed Fe2 could be from the shielded part of the cloud. So this will be the one of the topic I will be focusing on this in this talk. Then the other thing is collisional excitations. People also tried to produce lines to produce the observed spectra with the collisional excitation lines. But then there is a problem that if you use very high temperature, then you can produce Fe2, UV Fe2, but then there is a problem. You cannot get the lines of other metals. So that's why they refuse this collisional excitation. But there is possibility that it's a mixture of photoionization and collisional excitation. And there is also a possibility of mechanical heating. Mechanical heating, like when the clouds interact with each other, it can produce mechanical heating. Okay, so the third point is, what is the physical explanation for the correlation of iron Fe2, Fe2 emission with the other agent properties, like its addition ratios and the O3 emission? That we don't know. Okay, so it's very important to measure the Fe2 emission very accurately, and for that we use some templates. So there are two types of templates available. First is the observational template, which we call the empirical templates. So they are formed like you have the spectra, mainly the spectra of narrow line Seyfarts, because they have narrow lines, so you can easily identify each individual line. And then you remove all the individual lines and the continuum emission, and whatever residual is there, it's considered as a Fe2. So in this form, they make a Fe2 template. But there are issues with observation templates. First of all, they are limited by the signal to noise ratio of the spectra, and also the wavelength coverage, because there is no single template that covers from like UV to optical. And another issue is that those templates are only available for narrow line Seyfert ones, because narrow line Seyfert ones have narrow lines and you can easily identify it. But narrow lines cannot, it's possible that they are not the representative of the quasars. But people use those templates for the quasars also. So another category of templates are the theoretical templates. They are mainly based on the calculation of electronic transitions for each emission line. These are the examples. Okay, so the problem with theoretical templates is that is the atomic database. We do not have perfect or good quality of atomic database. So far, in this software called Cloudy, it's a photoionization code basically. It does the photoionization calculation. So in this software, the people uses very old atomic database, which is available. It's like from 1999, this database, which has very less atomic levels, very less number of emission lines, and also the highest energy level is 11.6 only. But recently, there are 3 different database available. So we use this Smith et al. Database in the Cloudy, which is the default database there, because it has energy up to 26.4 electron volt and so many emission lines. It's the latest atomic database. So what we are trying here, we use latest atomic database and we are trying to produce theoretical templates for Fe2. So how we did it? So first of all, we use the latest version of Cloudy, and we use a set of parameters, a complete grid, which has gas density from 10 to power 9 to 10 to power 14 per centimeter cube, and the ionization flux, photon flux, which ranges from 10 to power 17 to 10 to power 22. Hydrogen, we fix the hydrogen column density for 10 to power 24. And we use solar abundance for our standard model, but we also tried different metallicity. Then we also use the shape of the incident continuum, which is the default shape from the of AGN in the cloudy. It's look like this one here. And then we tried with different values of microturbulence. So what are microturbulence? They are random variations within the clouds, and it has values greater than the thermal motion, like more than 10 kilometer per second. And we tried different metallicity, like solar metallicity is 2 times, 5 times, and 10 times solar metallicity. Okay, so we have the model, but to compare our model, we need observed data. So for that, we use the quasar RM102. This is the composite spectra of quasar. This is the spectra mean combined using like 70 spectra of this source. And we overplot the mean spectra or the composite spectra of SDSS quasar. And you can see that it matches it perfectly represents the composite spectra of SDSS quasar. Although you can see here there is some deviation, it could be because of the calibration issue. It's at the edge corner of the spectrum. Yeah, also this side, both ends. Yeah. Yes. This one? Yes, it's reddening red side. Yeah. 24. It's fixed one. Yes. Yes, yes, yeah. Yeah. No, this is the column density for the cloud only. Yes. Yes. So we corrected the observed spectra for galactic extinction. Yeah. And also we tried for we tried like correcting for the host galaxy correction, but it's not very prominent. Mm-hmm. Okay. No, so the expectation is that whether our source is had the same structure as the composite spectra of the SDSS, or so that we can say that we have produced templates for a representative SDSS. For a representative quasar, which is similar to the SDSS quasars. On this data, because we have model now, we have to compare it with some data. Otherwise, model can produce so many results. Yes, yes, yeah. Yes. No, yeah. Okay. Yeah, this is. So this black one is our source that we are using, and the other one is, yeah, another one is composite SDSS spectra. So we are comparing whether our source spectra looks like the SDSS spectra or not. Yes. Yes. And another reason for using this source is that we have sufficient information about this, like the time delay for MG2, H beta, and the inter ratio. All these information we have for this source. No, I was just saying because you can see there is a departure. So one may think that it's not matching, but that departure could be because of the calibration, because it's at the corner of the spectrum. It's very possible. Yes. Yeah. No, there is just, yeah. Okay. Yeah, okay. So here I am showing the fitted spectra, the same spectra, but we have fitted with the power law, Balmer continuum, and the emission lines, all the emission lines. And those regions like blue, red, they represent the wavelength range that we are considering in our work. So in UV, we have the blue part of the UV spectra and the red part of the UV spectra. Wavelength ranges are given here, you can see. And why we have selected? Because in these regions, we have more Fe2. And this region is at the both side of the MG2 line in the UV. Similarly, here we have a blue part in the blue side of the H beta line, and this red one is the red side of the H beta line. And then we also mentioned here the equivalent width of this part of the Fe2, observed value. Now we will compare this with our model. So the first thing we compare with equivalent with our models, because we have model and we have a set of models, like the grade of models for different combinations. It's around 1300 something models. So now which model or which set of parameter is matching with the observed data? So for that, first of all, we need to compare the equivalent width or the strength of the line actually, or the strength of the Fe2. So these are the contours on each plot. X-axis is the density in log scale, and y-axis is the ionizing flux, that phi. And those contours levels are the value of the equivalent width from the model. But okay, one thing I should make it clear. The model has a geometry like plane parallel. It means that the source, the ionizing source is at the center and the cloud is completely covering it. So the covering factor is 100%, but which is not true for the actual or the observed data, which is for observed data, it's much less, like 20%, 30% only. So these values are for 100% covering factor. And I have made contours only for those values which are greater than the observed values, like this here. And the reason is because observed values are for actual covering factor, and these values are for 100% covering factor. So if you apply that covering factor correction, so these values, those observed one, they are the lower limit for the for these model predicted equivalent width. Okay, so now we have two different columns. This one is for turbulence velocity 0, when there is no turbulent velocity, only we have thermal motion. And this is for the turbulent velocity 100. We have calculated for other like 20 and 50, but I am showing just two for the comparison. So you can notice here, like this column. In this column, we have broadband, total, and this inward and outward. Okay, I'll clear what is total and what is inward, outward. So the inward is the radiation which is coming from the illuminated side of the cloud, or that means the front side of the cloud. And the outward is, which is the back side of the cloud, and total is the combination. Okay. Here we are testing that the full length suggestion that it could be from the backside or not. So what we notice when we include the turbulence, those equivalent widths are increased. Those values are increased for all the cases, like for all emission, total, blue wing, or the red wings in each and every case. So the thing is, if you add microturbulence, equivalent width or the strength of the line will increase. So the next thing we notice here, like for the outward case. So for the outward case, we see the region where the set of parameters which has equivalent width, observed equivalent width, is very small, and this is for 100% covering factor. If you use the covering factor much less, like 30%, 20%, you won't see it in this plot. So from this plot, we can say that even if we include turbulence velocity, for the outward case, we are not able to produce enough Fe2 to match the observed data. So Furland's suggestion that it could be from the outward phase, it's not true, at least for this source, we can say. How much is okay, so like here in this total, so the observed value is 306. Yeah, 305 point something, so 306. So here, this 306 is here. So if you like, this is for 100% covering factor. So if you apply like for 30%, so the value should be much higher here. And that value is not here in this plot. It will be. Yes. In here you can see. Yes, yes, yes. Mm-hmm. Yes. Yeah. I can try. Yeah, I can try, but yeah. One more reason, like the reason why we choose this 100 kilometers is that this much turbulence is predicted by those magnetically confined, pressure confined cloud model. They suggested that in their simulation, MHD simulations, they suggested that there could be turbulence of the order of few hundred kilometers. Yeah. Yeah, but if it is 1,000 or more than 1,000, then it's difficult. Like it's not microturbulence; it will be macroturbulence or more. Yeah, but then if it's 1,000 kilometer per second, then this is the motion, right? And yes. Mm-hmm. Mm-hmm. Yeah, but okay, so maybe I can try with 1,000. Yes. Okay. Yeah, it will just increase the equivalent width. Yeah, it will increase the equivalent width, also the shape of them. Yeah, it's 20% or 30%. Yes. Yeah. Okay, so this is the same plot, but for optical part. And here we have lots of problems because in optical, our photoionization model does not produce enough FE2. There is some problem. You can see because it's concentrated on very narrow part, narrow region. Here with the turbulence, it can increase the range, but still the values are very low. And again here also for the outward, we don't have enough rate. In this case, we don't have it. So it's like at least for this source, we can say the outward radius, outward FE2 is not possible to match the observed data actually, because if the uh, model is not matching the observed one, then there is no point of going further, like to compare the ratio of UV to optical. Okay, so the next thing is the shape of the UV FE2. If you see the observed spectra, this is the observed spectra. In that very high, in that UV bump range, like from 2,200 to 2,700, you will see the spectra is like this has some continuous in this shape. But in the standard photoionization model, you will see two spikes in this blue part. There are two spikes, and I will tell you why those spikes are there, because so the lines mainly formed in the illuminated part of the cloud, and in the illuminated part of the cloud, the optical depth is very low. So the yeah yes. So I yeah, here I mentioned the wavelength range for those two. Yeah, two wavelength range. So these are mainly from the UV1 and 2. UV1, this is from UV1 multiplet, and this is from UV2 plus 3 multiplet. Okay, so why these lines are there? Because these are the resonance lines. And because optical depth at the surface of the cloud is very low, and all the radiation, like energy, the incident radiation deposit all the energy in those lines. And they are resonance lines, like level 1 to level 2. So these features are very prominent. And the lines in this part, they are actually the high level lines. You need more energy to produce these lines. So this is the problem. And okay, so we will also see like how to solve this problem. And we also consider there are some ratios, some Fe2 ratios in our work. First is the ratio of spike to gap. The sum of these two spikes and this gap, and the wavelength range are here. And we also consider UV to optical ratio, the broad ratio. Here are the wavelength ranges. We consider the ratio of UV red to UV blue part, and similarly optical red to optical blue part. So these are the values of the observed values from the observed spectra. Yeah, singly ionized. Yeah. No, it's like goes. These lines are resonance, so it goes from level 1 to level 2. Yeah. Okay, so first let's start with the spike to gap ratio, because our in the observed spectra that ratio is very small. You can see the value. Value is 1.69. So we plotted the contours for that ratio, spike to gap ratio, from our model for different values of microturbulence 0, 20, 50, and 100. And those contour values, they represent the value of the ratio. And this red one represents the observed value of ratio. And the shaded region, this represent the set of models that predicts equivalent width corresponds to the observed equivalent width, or that are the favorable models. Because in the rest of the part, like in the white part, where this white part, it does not has it could not produce enough Fe2, which is compared to the observed data. So that's why we ignore that part, and we will only focus on the shaded region. So you can see our models has a wide range of parameters that can produce that observed ratio. This red line. And then we compare the UV to optical Fe2 ratio, which is from the observation is around 2. The value is around 2. But from models, you can see this value for our this favorable microturbulent velocity, 100 km per second, is nowhere in the picture. It's here somewhere, which is not the range of set of parameters which are not producing enough equivalent width of Fe2. So even with this new data set, it's we could not produce that observed ratio of UV to optical Fe2. So there is still some problem, or some problem with the data, or some problem with the model, because we are using the standard photoionization model plus microturbulence. Yes. So it has so many transitions, Like in that database which we are using, it has atomic transitions. Yeah. Yes. Yes, but it has, like in this database, we have, yeah, it's, no. So the levels are the 716 levels in the. Mhm. Mhm. Yes. No. So there are not like N1, N is equal to 1 to 2. There are some sub levels also, right? One. Okay. No. That is the electronic configuration. This is for FP2. This is for just electronic configuration. Yeah. So it's not like N is equal to one cell is for level is for N equal to 1 and 2. Yeah. Mm-hmm. Yes. Yeah. So yeah, their energy is so different that you can have from UV to NIR actually. Yeah. And they are very dense actually. So you cannot easily identify like there is one Fe2 line. Yeah. No. So there are like other also, because when you divide the levels into other, So there are other kind of transitions. Okay. Yeah. Yeah. So with this current atomic database, we could not solve this problem. So it's either because of the database is not has enough emission, enough atomic levels, or it could be that there are some other excitation mechanism other than the photoionization. Okay, then we also like plotted contours for red to blue ratio. The observed value is 1.9, and again, it's not like for our value of 100 kilometer per second, we cannot find this value in this our parameter range. And the one reason could be like because these people, their name is very different, so I can pronounce only first one, Kovacevic. And they suggested that it's possible because those red and blue part of the UV, they are Serbian, I think. Yeah. So they suggested that it could be possible that those two wavelengths or those two regions are from the different parts. So that's why they are not. Okay, so then we check whether there is an effect of broadening in the outflow which we are getting from the spectra. It could be because of the different broadening of the Fe2. So for that, we take one model for this value, phi is equal to 10 to the power 20.5 and density 10 to the power 12. And we applied a broadening of 2000 kilometer per second. And we found the peak in the UV range only, and it peaks at 2750 angstrom. Then we tried different values of broadening, starting from 500 to 4000, and different values of turbulence. So we noticed that with the turbulence, when we include the turbulence, there is a shift in the peak value with the broadening. And you can see there is, this is in the angstrom, like in the peak is in the angstrom, and this is in the peak in the wavelength velocity field. So you can see there is a velocity shift of 1000 kilometer per second, minus 1000 kilometer per second, which means outflow. So, and we did not include any other motion in the cloud, just the microturbulence. So with just varying the broadening of the region, we can produce an outflow of the order of 1000 kilometer per second. But we just tried with some single template. And this apparent velocity of 1000 kilometers is even is found by these authors in their paper. Okay, in the optical part, red to blue ratio, it's again very complicated because the observed value is 0.79 and the model predictive value shows that it's always greater than 1. This is the problem that I'm still working on. But one thing I want to clear here that this is for a single set of cloud parameters, like single value of density and single value of phi. But in reality, it's like it could be possible that you have Fe2 from different parts of the cloud with different density and different phi value. But since we are producing templates for different sets, so anyone can combine those templates for different, like for multi-zone cloud model to produce the actual spectra. Okay, let's come to this point, RFE2, because this is the main part for the quasar main sequence. It's actually the ratio of optical Fe2 in this wavelength range and the flux of H beta. And here we compare its value from two different database, and we found that its distribution peaks at around 0.6 for both the database. So in like this is the most probable value for the quasars, and the quasars like the A-type quasars or extreme population quasar for which RFE2 is greater than 1, they are very okay. So this Okay, so those quasars, they can be used for standard candles for cosmology. Okay. Okay, so in this plot, I have plotted contours for RFE2, and again the same different microturbulence velocities, and we can see that if we compare our models with the observed data, so those the values for RFE2, which is 1.24 for our source. So our source is kind of extreme population of A source because its value is greater than 1. So for extreme population A sources or for our source, those values lies in the either for this high value of density and high value of this incident flux. Again, we check the effect of metallicity. We have the contours, but here I am just summarizing the results with the table. And for three different turbulence velocity, three different values or abundance, and for two different positions, one with low phi value and the low density, and high phi value and high density. And we found that there is no such systematic trend for all the ratios we have considered in this source. So, so the conclusion could be that metallicity does not affect much to the Fe2. And okay, so these things are for when we include the turbulence in our model, not without turbulence. Yes. No, for all the composition. Yeah. Yes, it has enough iron. So earlier is yes. Oh yeah, because we include the turbulence in our model. So when we include turbulence, so even after changing the 10 or the values are not changing much. The ratios are not changing much. Okay, so the one reason could be because here we are estimating the ratio. So the effect will be same in both the wavelength ranges. So the ratio will not change. Yeah, this one is for broadband UV to optical, and this one is for UV for the red and blue part. It's very nearby, so it's possible that the ratio won't change. Okay, so here we are comparing. So yeah. Mhm. Yeah, so like our source, it has very high value of RFE2. So it's kind of extreme population A, and it has high attendance ratio. And for high attendance ratio, it's people suggested that it's possible that metallicity will be high. So yesterday there is a paper on archive, the second part of this work. There we have, but we have there we have used a different configuration. We have used, instead of constant density, we have used constant pressure on the cloud. And there we found that suggestion of high metallicity could solve uh, could produce the model spectra, which is matching with the observed one. So here we are comparing our model predicted spectra with the observed one. This gray one is the observed one, and the red one is the model predicted for different sets of parameters. They are mentioned here. These parameters are mentioned here, and we mainly we also estimated the value of phi from the spectra. We can estimate the value of phi from the spectra, because from the spectra we have this L nu, and then we can integrate this, and RBLR we know from the time delay of the source. So the estimated value of this flux is of the order of 10 to the power 20. And here we can see our model predicted spectra. Forget about this optical part, because it's not matching. It's not producing enough optical thing. So I will focus on this thing in my next project. But in UV, you can see it's matches not perfectly, but it's quite matches with the observed data in the UV part actually. And these model predicted spectra are for covering factor 20. We can change the covering factor, then the spectra will go up, let's say. Here we have used some different approach, because we see that people are using different templates for a UV part and optical part. So we are doing the same thing. We are for UV, we have used the template for 10 to power 5 values, 10 to power 20. We kept the density same, 10 to power 11 for both the cases. And for optical, we are using like 10 to power 19, 5 value. And we also use the different covering factor also. And because those people, Furlan and et al., they suggested that it's possible that the covering factor for optical part could be 50%. But here we tried like 20% covering factor for UV and 50% covering factor for optical. So the level increases slightly, but still it's not comparable to the observed data in the optical. It's all. Yeah. Yes. No, here, no. Here we have included the broadening corresponding to the observed spectra. So we, smeared that. Yeah. We smeared or we did the Gaussian smearing. Yes. So after subtracting all the lines. Okay, yeah. Yes. That dip is around MG2, yes. Underlined, yes. So that's the problem with the observed templates, because you cannot estimate the FE2 underline the emission line. But with theoretical template, you can estimate, because it's from the calculation of the transitions. Yes. Yeah, because it's underneath the line. Okay, so yeah, so the advantage I already told that with theoretical templates, we can estimate the FE2, which is underlying the any individual line. And this one, I already discussed that most of the observational templates are made for the narrow line Seifert sources, mainly for this source, 1ZK1. And recently, there is a template for this source also, Markarian 493. And these narrow line Seifert ones, they have very high Denton ratio, and they have very high FE2 emission. But they are not the representative of quasars in general. Okay, and we see that even we are using the latest atomic database, we are unable to produce that UV to optical ratio, which is similar to the observed one. So the problem, like people suggested, it could be because of the reddening, increasing reddening. But even with the highly reddened sources like this factor increases by a factor of 4 only. But in our case, the factor is much higher, like 10 or more. Mechanical heating, we have this thing we have studied in our next paper. And we found that this heating only affect for low phi value. At high phi value, like around 20, it has not much effect. And so the first weakness, which is in the standard photoionization calculation, is that we are using constant density. But the problem is, because the temperature at the illuminated side is much higher compared to the back side. So there is a gradient of temperature, and you will see there is a, the density will not be the same. But okay, so in the next work, we tried with the constant pressure thing. And the second problem, the problem of heating, we already did this, and the heating only affects the low phi value, 10 to the power 18, up to 10 to the power 18. But at 10 to the power 20, it has not much effect. Okay, and here we have produced templates for so many sets of like phi and NH. So people can take this and combine with any multi-zone model to produce some observed spectra. There is one such model, this called locally optimized model, LOC model, locally optimized cloud model. Okay, so these are the conclusions. I already discussed this. And these templates are available at this link. It's my GitHub link. If anyone wants, can use this one. And this is the paper. It came yesterday on archive. So here we use different approach, constant pressure, like the constant pressure within the cloud. And we tried different geometry as well, like two different clouds. Emission is coming from two different clouds and also from two different parts, like from 20% from the dark side, 80% from the illuminated side. It means different geometries. And we also tried different values of metallicity. Here we goes up to 50 times the solar metallicity. So we found that for our source, the metallicity can be higher because it's a extreme population source. Okay. Individual element. No. It's metallicity, overall metallicity, the cloud for each component. Yeah. For different elements. Yeah, could be. But we have, yeah, I didn't try. Yeah, yes.
Does this works have any comments on the changing look agents? Because
not on changing look agent, but recently I did some work on changing look blazar.
okay.
So what I noticed, there is something interesting. So in changing look blazars, they are not actually changing look blazars. People call it, but recently I worked on, and the conclusion is that they are not changing look blazars. They are the FSRQs. They behaves like a BLX on the high states. So the interesting thing is, so when you see their spectra in the low state, and when you compare the Fe2 in the low state and the high state, so the comparison is the Mg2 line, because in that source there is a Mg2 line, it's a high redshift source. So the Mg2 line of flux is decreased, continuum is increased in the high state, but the Fe2 flux increased, which should decrease because it's if it is coming from the, like if it is photoionized from the disk, but it is increasing. That means it is affected by the jet emission. So it indicates that that Fe2 could be aligned our line of sight, because jet is towards our line of sight. So it may indicate that those Fe2 region is along our line of sight, but not from radio, not from the changing look field. Not Scar, that I was trying to. No. So like for combining the cloud side, so I used this Prado model, and for few like 200 sources, 200 cloud positions, and I combined all the like the cloud solutions for 200 clouds. So there is a change like in the optical part. So that ratio now goes similar to the optical red to blue ratio. It's similar to the observed one when we combine the clouds. So that's the that is what I am. Number of cloud positions are very high, like 10 to the power 6 or 7. Yeah, it's computation problem. I need to estimate cloudy solution for all the clouds, 10 to the power 6. But I am thinking to remove the clouds which are unable to produce enough radius, enough emission lines. because that range of phi is around 10 to the power 17. So the crowd position for which the phi is less than 10 to the power 17, that I can remove. Yes, yes, the distance. But Pareto is like kind of wind, like outflow and out. Yes. Yeah. So I'm thinking to like combine, this code where they have this kind of geometry in BLR, but they only applied this to H beta line. But then there are, the brain code there, brains code, right? So if, because there are now observations of carbon 4 that has outflow. So we can also add the outflow kind of geometry in that configuration. Thank you.